So this is a little micro lecture on chemistry review as it pertains to physiology. So let's get right into it. All right, atoms. So atoms are made of protons, neutrons, and electrons. And so you hopefully been exposed to the periodic table of elements. And so we're going to look at some of these elements. And each one of these elements, like hydrogen, is going to have one proton and one electron. And atoms also have something called a neutron. And so it's also going to have one neutron. And so atoms have an atomic number on that periodic table. And so hydrogen has an atomic number of 1. So it's got an atomic number of 1, and that means it has 1 proton. So the atomic number is equivalent to the number of protons. Number of protons are equivalent to the number of electrons and neutrons if it's an electrically neutral element. So it should all be equal. And when we talk about protons and neutrons kind of hang out here in the nucleus. So this right here is a proton. And then the electrons hang out here in what's called the valence or valence. So these are electrons. So if hydrogen has 1 proton, it's only going to have 1 electron, right? So if this were hydrogen, you'd have 1 proton, you'd have 1 electron, and then you'd have 1 neutron. It doesn't have a charge. So the neutrons are going to be these neutral looking things. This is significant in physiology because we have ions in our body, and those are elements that have gained or lost an electron. And so they now have a charge. So ions of charged particle, and we're going to talk about that in a minute. But I want to explain to you what protons, neutrons, and electrons are. And so all of your body, the human body, is about 99.3% hydrogen, oxygen, carbon, and nitrogen. So that is the main elements of our body. Hydrogens can become an ion. Oxygen, carbon, and nitrogens tend to form polar bonds with ions. So other minerals that make up that 0.7%, calcium, phosphate, potassium, sulfur, these are things you need to get in through your diet. So that's where those are needed. The atomic weight is equivalent to the atomic number, and the atomic number is equivalent to the number of protons in the element. So example, hydrogen, again, it has 1 proton. So it's going to have atomic number 1. It's also going to have 1 electron and 1 neutron. Okay, so that would be an example of hydrogen. This is an electrically neutral element because it has 1 proton, 1 electron, 1 neutron. But hydrogen can very easily give up its electron, in which case, if hydrogen has a proton and an electron, but it gives up the electron to, say, chloride. Now, chloride is gaining the electron, and hydrogen is losing its electron. And so now hydrogen just has 1 proton. And so that's why you see it has a plus. Chloride has an extra electron because it has hydrogen's electron. Now they become ions. They are no longer neutral. So an ion, not a neutral element or atom. So this is also why we call a hydrogen that gave up its electron, we call it a proton. So you're going to see in physiology, we call a hydrogen that gave up its electron a proton. Normally, electrically neutral, which means the number of neutrons are equal to the number of protons. But in the case of ions, it's an ion gave up an electron or gained an extra electron or two. You can see like calcium has a +2, which means it gave up 2 electrons and now has 2 extra protons, more than it has electrons. There's something also called an isotope, and we're not going to really talk about this in physiology at all, but I'm just going to describe what an isotope is. So this is carbon, right? There's 12 electrons because there are 12 protons. And then there are going to be 12 neutrons. All right, so it's 12. But if for some reason carbon now has 8 neutrons, it's no longer equal, right? It's 2 more neutrons. And that is what an isotope is. An isotope is less stable. That's what radioactive really is referring to. It's not as stable because it's no longer equal. When things aren't equal, they become unstable. So like you have a seesaw, right? And this would be 6 and 6. But if it now has 6 and 8, what's going to happen here is it's going to look like this. So it's no longer equal. 8 is going to weigh more, right? So it becomes less stable. That's what a isotope is. Won't talk about that again. Just thought I'd give you an FYI. But as I was alluding to, ions are an atom that has either gained or lost 1 or more electrons. So it's no longer neutral, right? It's going to have more protons or more electrons, right? So atom that now has more electrons than protons, that would make it an ion, or it has an atom that has more protons than electrons, and that's going to equal a cation. So you're going to see right there ions that have a net positive charge. Why? Because it gave up its electrons. So cations are said to have given up electrons, right? So has more protons than electrons, right? So that's where it says has more protons than electrons. And so that's why you see a plus, because the plus is for protons, right? And so protons, more protons than electrons. So calcium is going to have 2 more protons than it has electrons, meaning it gave up. Calcium gave up 2 electrons. Now, if it's sodium, sodium just has a plus right there, so it only gave up 1 electron. Anions are going to be the opposite. Anions gain electrons, right? So they're going to have more electrons than protons. And so it gained an electron, So now it's going to have one more electron than it has protons, so it gets a minus charge, meaning it has one extra, right? So one extra electron. These become charged particles, and because of their charges, ions can move, right? So if you have a membrane here and you have a bunch of anions on one side and you have a bunch of cations on the other, and you were to open up this membrane, right? The pluses and minuses are going to move towards each other because there's an attraction. And when charged particles move, that is what we call electricity. And so in physiology, this is really important to have all these ions because this is what's going to keep your nervous system generating action potentials or electrical currents. So table 2.2 goes over the most common ionic elements in the body. And so you can kind of peruse through these. You see hydrogen's very common, sodium, potassium. This is a +1, that's +1. So all of these have given up an electron. Chloride is going to be a minus, so it gained an electron. And then magnesium and calcium gave up 2 electrons. And so they become ions. And I should mention one other thing. When there are ions, there's something called an ionic bond. And that is because cations and anions are attracted to one another. And so you've seen this, right, with sodium chloride. Sodium is a cation, chloride is an anion, and these two things form an attraction, so keep sodium next to chloride. And this is what we would call a polar molecule. It's an ionic bond. Okay, so when you have two or more atoms bonded together, it's a molecule. So again, we have sodium chloride. This would be an ionic bonded molecule. But you can also have covalently bonded. So like glucose. So glucose would be 6H12O6. So that would be a covalently bonded. Oh, I got it down here. There you go. That's glucose. What does it mean? It means there are 6 carbons, 12 hydrogens, and 6 oxygens that combine to form glucose. So there's a carbon, 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 carbon. And then off this, you're going to have hydrogens and so forth. I won't draw the whole thing out, but you get the gist of it, right? So you're going to have some oxygens in there and so forth. So you're going to end up with 6 and 12. Okay, so I mentioned ionic bonding, and then I mentioned covalent bonding. And so ionic bondings are attractions, right? They're attracted to one another. Ionic bonds are really attractions. They can be, separated really easily. They're attracted to one another, but if something more attractive comes along, they'll break up, right? Covalently bonded, much stronger. It means there's an actual bond, right? Instead of just dating, you have an attraction, you actually get married. Now there's a legal contract. You're covalently bonded. So this is showing you a methane. It's a carbon that actually forms equal sharing of electrons, which is a covalent bond, with hydrogen. So it's 4, so it would be CH4. So that's methane right there. And so it's kind of showing you, here's the carbon, right? You have the 6 protons, and then you have 1, 2, 3, 4, 5, 6 electrons. And each one of those electrons in the outer shell are going to then bond with the proton of the hydrogen. And so each one of these is going to be a hydrogen out here. Equally shared electrons and protons, and that would be a non-polar covalent bond. Everything's equally shared. But there's another type called polar covalent bonds, where the electrons hang out closer to one atom more than the other. Okay, so that would be polar. The electrons are going to be closer to one, and then the proton is kind of separated from that electron, and so it takes on a little bit of a charge. Nonpolar, the electrons and protons are equally shared. We'll get to hydrogen bonds a little bit later, but let's talk a little bit more about polar and nonpolar. I'm bringing up ionization. Again, we talked about the process of gaining or losing. So that's ionization, right? And it can happen in a single atom. It can occur in atoms that are covalently linked, right? So it would be polar or polar covalent bonding. It can also be reversible. So this is really common in physiology. Carboxyl groups and amine groups, which are the building blocks of proteins, these commonly undergo ionization. And so you can see these ionized groups right here, the carboxyl groups, the amine groups, phosphate groups for like ATP has this high inorganic phosphate group. And so when you see nonpolar and polar, I just want to mention these ionized groups, you're going to see these a lot. Polar covalent bonds, the number one thing is the electrons are not shared equally between the two atoms. Instead, they're going to stay closer to one of the atoms. And so this produces a slight charge, right? So you're going to have a slight charge. One's going to be more slightly negative, and the other atom is going to be more slightly positive. And so this is just kind of showing you a polar covalent bond. This could be any kind of number of molecules, but it's showing you that the oxygen is taking on a slightly negative charge where the hydrogen is taking on a slightly positive charge. And so polar covalent bonds form polar molecules. And polar molecules have charges to them. That's going to be different than nonpolar molecules, which have no charge. And so all things are shared equally. It becomes almost like a different substance. So polar covalent bonds, again, things to remember is that one's going to be more slightly negative, one's going to be slightly more positive, takes on a slight charge. And so oxygen, nitrogen, and sulfur have a kind of an attraction for electrons. They pull electrons towards them, and they tend to form polar bonds with hydrogen. And so another thing that is really important is that molecules with polar bonds tend to be more soluble in water, meaning they can dissolve or exist in water. Now, a large part of our body is water. And so we need molecules physiologically in our body to get along with water because our body's mostly water. And so most molecules in our body are going to be polar molecules, especially those that are in fluid. So any kind of molecules kind of cruising around your blood, interstitial fluid, intracellular fluid are going to be polar molecules because they're going to be able to get along with polar molecules. And this is really important when we talk about the cell membrane and a phospholipid bilayer, because the phosphate heads are polar. They get along with polar water. The lipid inner lining or lipid tails of the cell membrane or plasma membrane is nonpolar, and it's not going to let polar molecules through. So we're kind of reviewing all this stuff. So when we talk about polar, nonpolar, it's you kind of have a refresher. Okay, so nonpolar, everything's equally shared. Electrons, protons equally shared. So it's a nonpolar covalently bonded molecule. And the take home here is they are not soluble in water. Think about this. Nonpolar tends to be things like oils, fats. Those are nonpolar. Polar is like water. Now, anyone that's tried to mix oils and or fats and water realizes it doesn't mix, right? If you were to take a container and you put polar water in here, and then you add some oil here, which is non-polar, even if you shake it, right, and you try to mix this, you shake it up, if you let it sit, it might kind of mix a little bit, right? So you may get it to, so you mix, and you might get something that kind of looks like this. So it might mix a little bit, but if you were to let it sit, what's going to happen? It's going to go right back to being separated. Why? Because polar and non-polar molecules do not like to mix. And so polar molecules cannot really, without a lot of energy being put into it, like mixing or shaking, polar molecules cannot go through a non-polar substance. And so again, when we talk about the phospholipid bilayer, if we're looking at a phospholipid bilayer, this is just a preview. Here are the phosphate heads, and then you're going to have the lipid tails. And so this is making up your cell membrane, right? And so if you have all these polar molecules out here plus water, right, because you have intracellular fluid and extracellular fluid, right? It cannot go through it. It gets along with the phosphate heads, right? Because these are polar. So it's chilling. Phosphate heads get along great with water. And so they're fine, but nothing can go through that lipid layer, right? So only things like gases can go through the lipid layer or nonpolar substances. So it's a great barrier because extracellular fluid, intracellular fluid are both polar. Another thing with hydrogens, or when two polar molecules are in close contact, there can be an attraction or a weak bond formed with the hydrogens, right? So the hydrogens can form what is called a hydrogen bond. They are weak, but they do play a role when present in large numbers. That's why water, like if you were to dump a little blob of water onto a desk, right? So this is just a little water molecule or a water drop. That water drop tends to stay together. Why? Because of hydrogen bonds. They're weak though, so if you kind of spread that water out, the molecules will separate. But it's really the hydrogen of one molecule kind of forming a weak bond with the oxygen of another. And that's what a hydrogen bond is. So we see this hydrogen bonding. It plays a role in protein conformation. So we're going to talk about protein conformation, hydrogen bonds being attracted to an oxygen or nitrogen next to it. Another concept in chemistry to quickly go over is solutions, right? Since 99% of our physiology is water, water is going to be the solvent. So in our body, water is the solvent. And we're going to have a lot of solutes, which are substances dissolved in there. And so it could be glucose, it could be sodium, it could be potassium, etc. Right? So we have a lot of things that are solutes. That's the things that are dissolved in the liquids. They tend to be polar molecules. Why? Because if they were nonpolar, they would not dissolve. So only polar dissolves in a solvent. And when you have a solvent and solutes, it becomes a solution. Sorry about that. So a solution is solutes. Oh, it says it here, dissolved in solvent. So again, if you have water and you put table salt, which is sodium chloride, this is ionic bonded, which is weak, and you put that sodium chloride into water, they're both polar. But what's going to happen is since the ionic bonds are weak, the sodium is going to become attracted to the oxygens of the molecule, of the water molecules. Chloride is going to be more attracted to the hydrogens. They're going to separate, get surrounded by these polar water molecules, and we say it dissolves, right? Did I say 60% of total body weight? Okay, so hydrophilic means lover of, and hydro refers to water. So hydrophilic molecule loves water. It's going to be a polar molecule, right? Hydrophobic, phobic means fear of, right? So it's going to be water fearing. And these are going to be polar, non-polar covalently bonded. So these are going to be, fats, oils, lipids, cholesterols, etc. Right? And so hydrophobic means, generally speaking, non-polar. Oops, molecules. I'm really starting to have problems writing. Okay, so water moves between fluid compartments. We kind of talked about this in chapter 1, right? We have membranes and they separate the body into compartments. And so things have to kind of flow between those compartments. And the way that water moves is called osmosis. And so osmosis is a process in which water moves. Now, water is going to move from regions of low solute concentration to regions of high. So water moves up the solute concentration gradient, and we are going to talk a lot about this in physiology. So this is just a preview. We're going to get more into transport, cellular transport. We're going to talk about osmosis, and we're going to really use this concept throughout all of physiology. So this is just kind of prepping you. Osmosis, the direction water moves, and water always moves up the solute concentration gradient. A few more things. Amphipathic molecules. Amphipathic molecules are basically molecules that are going to have a polar part and a nonpolar part. So a perfect example is the plasma membrane, right? You're going to have the polar outer layer and you're going to have the nonpolar inner layer, and then you're also going to have a polar outer layer that makes up the plasma membrane. So it's ambipathic. It just means that there's polar, nonpolar. We have carrying proteins that are going to be ambipathic because you can't have a nonpolar structure floating around in your blood because your blood is mostly water or plasma and it's polar. And so you have to kind of, if you have a nonpolar molecule, you're going to have to coat it with a polar molecule, right? And so it becomes ambipathic. So I'm just introducing this term ambipathic. Two other things, concentration. Concentration is expressed as the amount of solute dissolved in a liter of solution. And so we tend to use these brackets for concentration. So if I have this is going to say, and I'm already not spelling, so let's try that again. Concentration of sodium in blood, right? And so that would be per liter of blood. So these brackets right here, this means concentration of, and concentration of whatever the solute is going to be denoted in the center. And sometimes you can see what the solvent is. And so that would be the solvent in this case. So concentration is the amount. If it's a high concentration, it means you have a lot of sodium in the blood. You have a high concentration. A low concentration would be less. When it comes to pH, we talk about acids and bases. An acid is the concentration of protons in a solution. So an acid is based on the concentration of protons, which are hydrogens that have given up an electron in most cases, plasma. We're talking about the pH of our blood. So if there is a high concentration of protons, then it's going to be acidic. Bases have a low concentration of protons and it becomes a base. Also, we use bicarbonate. And so bicarbonate, you'll see it's common base in plasma. So you won't be getting to that anytime soon, but acids and bases are kind of based on the amount of or concentration of protons, or it could be bicarbonate. This is bicarbonate. Water, again, we not only use water as our solvent, right? Plasma and interstitial fluid and intracellular fluid. These are all water-based, right? Water's super important. They're polar molecules. And between 0 to 100 degrees centigrade, it's stable, right? It's a fluid. If it goes 100 degrees centigrade, the bonds become weak and it starts to become a gas. If you get below, and this should be 0, so we'll pretend that's a 0, it becomes crystals, and we call that ice, right? Um, we use water not just as a solvent, but as a solvent in chemical reactions. And these chemical reactions are called hydrolysis. We're using water to break down large molecules into small molecules. So another way to write this is hydrolysis. Water is used to break down a large molecule into smaller molecules. Okay, so we're using water to break apart molecules. Dehydration is where we're actually pulling water out. And so dehydration and condensation are basically, for our purposes, the same. It's where you're taking two molecules and two separate molecules, and you're pulling out a proton from one and a hydroxyl group from another to form water. And in the process, you combine the two molecules into one molecule. So condensation, dehydration is where two molecules combine to form a larger molecule with the loss of a smaller molecule. That is water. Basically, you pull water out or dehydrate two molecules when combined into one larger molecule. So this is super common, and you'll see this in biochemistry. You're going to see it in cellular respiration. So very common. All right. One last slide, which I want you guys to write down the definition of a cation, anion, polar, nonpolar molecules. Give an example of each and bring it to class. I also want you to define osmosis. And then answer the question, why is it important? Why are all these things important when it comes to physiology? Write it down and bring to class. This way I see if you're watching lecture. All right, that's it for now.